Assalamualaikum everyone. So we are from group 5. We'll be presenting our group project entitled Flash Design to Separate Pentane and Hexane. So I hope you guys will enjoy this video. Let's go. The overview of this video is we're going to talk about the background, the objective, the introduction for what is a flash column. Next, we're going to talk about the typical process condition, which is the common properties like pressure or temperature that we need to use to separate the hexane and pentane in a flash column. Next, we're going to show you how we calculate the process, and also we're going to conclude what we learned from this project in the conclusion, and also the references that we use in this project, through this project. So let's go to the background and objective.
This project is a part of chemical engineering thermodynamics, focuses on development of a flash system for separating binary mixture. Our group has been tasked with separating pentane and hexane. This study is critical for understanding thermodynamic concept in practical application, notable in chemical engineering processes that need component separation and purification. For the objective, our main objective is first to construct the process condition such as overall composition, operating pressure and temperature, and also we want to determine the mole of liquid and vapor and their respective phase mole fraction.
Hi, I'm gonna explain about the introduction of what is a flash column. A flash column is a cylindrical tube filled with a stationary phase, typically like a silica gel or alumina, that designed for the rapid separation of compounds in a mixture. So, the mixture that we use in this project is hexane and pentane. The process involves dissolving the sample in a solvent and applying it to the top of the column. A pressured diluent, often delivered via a pump or compressed air, forces the solvent through the column, speeding up the separation compared to the traditional gravity-fed methods. As the mixture passes through the stationary phase, its components separate based on their differential interactions with the stationary phase and their solubility in the diluent. The separated compounds are then collected in fractions at the column's exit, and making flash chromatography an efficient method for purifying reaction products in synthetic organic chemistry.
For the typical process condition, first, the mixture composition that we assume for the feed composition is 45% pentane and 55% hexane by mole. Second, the pressure for flash distillation should be selected based on the vapor-liquid equilibrium data of the component. For this case, the vapor pressure data for pentane and hexane was 100 kPa. Third, the temperature is often determined by the boiling point of the component at the chosen pressure. For pentane, the boiling point at 1 atm is 36 degrees Celsius, while hexane, the boiling point at 1 atm is 69 degrees Celsius. Hence, after comparing temperature range for both species, the temperature chosen for this process is 50 degrees Celsius. Then, we also assume that the reaction mixture behaves as an ideal solution.
Hi, my name is AMIRAH ALIA BINTI AFZANIZAM, and I will be explaining about the flash calculation. So I will be explain a part of it, and AFIFAH will continue for another part. So in this system, we have two species, which is pentane and hexane, at 50 degrees Celsius and 100 kPa. It has overall composition, which is Z1 is 0.45 and Z2 is 0.55. So we will be assuming the Rod's law is appropriate for this system. So we need to determine the K, L, V, and also mole for species 1 and also mole for species 2. So first we need to find the P saturated for species 1 and species 2. So the formula that we use is ln P sat equals to A minus B over T plus C. So T that we use here is in degrees Celsius. A, B, C we can find in table B2, which is Pentane equation. So in this calculation, we will get P set for species 1 is 159.57 kPa and P saturated for species 2 is 54.6. So next, we move on to P dew and P bubble. So we already set 100 kPa for this system, but we need to ensure that the 100 kPa is between the P dew and also P bubble, which is a two-phase system. So for P bubble, we will use the formula of sum of Xi times Pi saturated. So the total for P bubble is 101.83 kPa, and for P dew, since we assume that all vapor, so V equals to 1 and L equals to 0, and also Zi equals to Yi. So for P dew, we got the sum of 77.56 kPa. So since the pressure that we set, which is 100 kPa, is between 77.56 and also 101.83, so it is a two-phase system. Next, we move on to find the Ki. So the formula is Ki equals to Pi saturated over pressure that we put, which is 100 kPa. So for K1 is 1.5957 and for K2 is 0.546.
So now we have to find the V using the formula of summation of Zi Ki over 1 plus V in the bracket of Ki minus 1 equal to 1. Since we already have the value of Z1 and Z2 and also K1 and K2, we just have to input everything into the formula, and then we'll find out that the V is 0.0332 mole. Next, we have to find the L using the formula of L equal to 1 minus V, and then we'll just include the previous V that we already got, and we will get L equal to 0.9668 mole. And then we have to find Y1 and Y2 using the formula of Y1 equal to Z1 K1 over 1 plus V in the bracket of K1 minus 1. Again, we just have to input the number into the formula, and then we'll find out that the Y1 is equal to 0.7041 and Y2 is equal to 0.3049. And lastly, we have to find X1 and X2 using the formula of Xi equal to Zi over 1 plus V in the bracket of Ki minus 1. We'll find out that X1 is equal to 0.4413 and X2 is equal to 0.5587.
The conclusion that we can make from this project is the flash column design is made to separate two different species to the bottom pipeline and upper pipeline, based in the mole of the species, the temperature and pressure set, and also the pressure saturated of the species.